Right, so here's our mass on the spring again, but we're looking a little bit later in its motion. So it's not right at the beginning, it's just somewhere along the way. Let's look at a few key points in the motion here. So at this lower spot, this would be a spot where the spring is being stretched to its maximum, and that large force that it is exerting on the mass is slowing it actually to a stop. And so the object has a velocity of 0 at this point, and notice that the v is 0 here, where the x is at its maximum. If I look at the next sort of part to its cycle, this would be a quarter of the way through the period past the first point. At this point, the net force is 0. And so there's no force on it, there's no acceleration. This is where the object is just moving through the central point. The spring was accelerating it towards that point, but now it's going to be about to begin to decelerate it. So this is where the object has its highest speed. So again, notice how we're at the 0 point of x, but our speed is at its maximum. There's this oppositeness to that. Then when I reach the highest point, the force again becomes large. This is where the spring is going to be as compressed as it possibly can, and so it's going to be exerting the biggest compression force that it can, and it's going to bring that object completely to a stop before it turns around and goes back. So v is at its minimum when x is at its maximum. And then in this next spot here, so this would be 3/4 of the way through the period. This was 1/2 through the period. So 3/4 of the period, we are again moving through a point of highest speed, but 0 position, but now just moving downwards. So hopefully you're seeing how there's this, kind of same cycling of the velocity, but it's a little bit off. It's off by like a quarter of the cycle. Well, we can actually analyze this using some derivative ideas, some calculus. I'm just going to go through this real quickly because I know some of us are not in calculus right now. So this is another pattern of derivatives that we need to know, and it is described on the back of the formula sheet. So if you need to refresh your memory there, or after we talk about this, you can. But the idea is that if cosine is the function that describes something's position, then the velocity of the object is like a cycle off of it, or a quarter cycle off of that. And so that ends up being the sine function. So when the cosine is at its maximum, the sine function is 0. When the cosine is at 0, the sine function is at its maximum or minimum point. So that exactly matches this idea of how position and velocity relate. So that should make sense. But again, this is just a type of derivative that we need to be familiar with. The derivative of the cosine function is -1 times the sine function. And the derivative of the sine function is just the cosine function. So it doesn't always have that negative. Again, if you forget those rules, look at the back of the formula sheet to help you remember them. Now, our cosine functions and sine functions, they are going to have a number in front of t that's going to represent that angular frequency omega. And so we're going to have to know what to do with that. What you do is you take the derivative of what's inside, so the derivative of 3t would just be 3, and you multiply the whole result by it. So the cosine of 3t changes to -1 times the sine of 3t, and then we also multiply by the derivative of what's inside the parentheses. So it's -3 sine of 3t. This next one here, this is the sine of 5t squared. So, the basic look of it is when we take the derivative, it switches to just a cosine function, not a negative, which is a cosine function. But then I also multiply by the derivative of what's inside. This isn't exactly what we're talking about now, but again, it might come up later in the course. Derivative of 5t squared would be 10t, lower that exponent by 1, and so our derivative is 10t times the cosine. So that's going to help us understand a little bit about why we saw what we saw when we considered the position and the velocity, if I start with just kind of a general formula for position, x equals amplitude times the cosine of omega t, if I take the derivative of this using those rules, the cosine switches to the -1 times the sine, and then I also take the derivative of what's inside. Omega is just going to be a constant number that describes the rate at which a particular object is oscillating. And so that constant number times t, when I take the derivative, is just that constant number. And so that's why this omega shows up here. So I've got the v function overlaid on our picture here in green, so that you can kind of see the pattern that we were talking about. How when I say look at this point here, where my position function is at a maximum but a negative maximum, that should correspond to a 0 speed. My object stops for a split second. And sure enough, the negative sine function, the green line, is 0 at that point. If instead I look over here, where my object is passing through the equilibrium point, so x is 0, this is a point where my velocity should be at its maximum, and it should be negative. This object is moving downward. And sure enough, my green velocity function it's at a maximum value, but in the negative direction. We can do the same thing with an acceleration function. If we take the derivative one more time, then that sine function's derivative just becomes cosine. It doesn't change whether it's positive or negative. So it just remains negative. And then I take again the derivative of what's inside the parentheses, which is omega. And so outside I end up having omega squared. So important thing to notice here is that the cosine function that I started with for position, now I'm looking for acceleration as the opposite of that cosine. And it's a different size because it's a different constant number in front. Okay, but it follows the same period. Okay, it has the same cycling. It's just opposite. Okay, so the negative sign here just means that when the position function is low, then the acceleration function is high. And when the position function is high, then the acceleration function is low. But they're both 0 at the same time. And this makes sense with what we learned about Hooke's law. Acceleration would match what a force is doing. And since Hooke's law tells us that if the object moves to the right, there's a force trying to restore it to the left, there's this opposite direction of force and displacement, then it makes sense that there should also be this opposite direction to acceleration and displacement. Again, we can see that by looking at a couple of examples. Here's a spot where they're both 0. Okay, so if there's 0 displacement, then there's 0 force, so there should be 0 acceleration. But if over here, where there is a negative displacement, then I should have a positive force and a positive acceleration, which I do. Now, there is kind of just one more connection that we'll see here, and that is just to kind of go through and do a little algebra with these two things. So I have here side by side the two functions x and a, and here I've just rearranged the a function, the acceleration function, so that you can see how this capital A cosine omega t is actually embedded within the acceleration function. And so we can replace that with x. That's all that, capital A cosine of omega t is x. And so we get this general relationship that the acceleration of the object is equal to -1 times omega squared times the x function. And we'll see later on how that's really important for understanding various situations.